Hello there. So this is a very exciting video because here we are going to introduce matrix multiplication. This is a very non-intuitive operation, but with very good motivation for why it is defined the way it is. And so really all I want to do is I want to give the motivation for why it is defined the way it is, give the formal definition of how we multiply matrices together, give the much better way of actually sort of thinking about how to do it. Much like vector matrix multiplication, it involves a dance. And then we're going to calculate some matrix products and go over some important warnings about matrix multiplication. So, one of the main things we introduced towards the end of chapter 1, remember, was that we can actually think about matrices as linear transformations. So for example, if this matrix B is an n by p matrix, remember, we can think about B as a linear transformation from Rp to Rn, where I take each vector in Rpx and multiply it by B to get a new vector, B times x in Rn. So much like we have done with functions, because these matrices are kind of acting like functions in this case, we can compose them. And so what I have on the board behind me is the composition of sort of two functions that are the matrices A and B. So what happens is B takes x, acts on it by multiplication, and sends it to a new vector, B times x in Rn. Well, now since A is an m by n matrix, A can act on this vector, B times x in Rn, and send it to a new vector in Rm. And so notice here I have the vector A times B times x. But what if we wanted a single matrix, which could instead just do this sort of composition of maps in one single map, right? So I wanted one matrix that will send x in Rp to this vector in Rm, and it turns out this matrix is going to actually be the matrix A times B. So in order to figure out how to calculate A times B, we need to ask, okay, what's going on in these compositions, and what am I actually getting here? So, first things first, if these are the columns of B, right, so if we define B this way, then B times x is equal to B1 times x1 plus B2 times x2 plus BP times xp. And so in particular here, these b's are the columns of B, and the x's are individual entries of the vector x. Right? So these are scalars or variables depending on what type of vector we're looking at, and these are column vectors. So that's B times x. Now, A times B times x, calculated in this way, well, this is A times this big sum, but if you'll remember, I actually can distribute matrices across vector sums. So this is actually equal to the following. This is actually equal to the following sum, where I've just distributed A across each of these terms. And so notice, this is the vector we're getting in Rm, right? But I want to somehow be able to express this vector as now, I want to kind of pull out the information from this vector to figure out exactly what this product should be. But notice, by the way this is defined, this looks an awful lot like the product of some matrix and a vector x, and it turns out it's the product of this matrix whose columns are given by the vectors a times b1, a times b2, times this vector x. And so this matrix here is the matrix A times B. So I'm going to write this definition down formally. And then, like I said, this isn't my preferred way to think about how to actually do matrix multiplication. I'll give you my preferred way of sort of doing it. And like I said, it involves a dance. And then we'll just do a bunch of matrix products. But it's sort of an odd, like you'll see when we're doing it, it makes sense, but like, I guess it is a little weird. And so it is nice. I think, the first time I kind of learned, because I think I learned how to multiply matrices before learning the motivation, which I just talked about. And it was nice for me to know, like, okay, there's a very good reason for why it's defined the way it is. All right, so definition. And so this is just sort of restating what I've stated here. Then A times B is equal to the matrix whose columns are given by the following vectors. Again, A times B1, A times B2, A times BP. And so this is the actual product of A times B. All right, so let's do an example. Then I'm going to make a few notes about what we know about the product. We'll do another example, and then I'm going to give a warning. So how do we multiply actual matrices out? All right, so let's say I wanted to multiply the matrices. -1, 5, 2, 2, 4, -3, times 3, -2, -2, 1. All right, so what you do is you start with the first row of A, much like the vector dance. You take the first row of A, match it up with the first column of B. So you do da, 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 da. And what you do is you multiply all of the entries which match up. So I would take -1, 2, match it up with 3, 2. So I would add -3 plus -4 to get -7. Then what you're going to do is you're going to work your way down the row, or sorry, down the column, and continue to, so you're going to work your way down column 1 as you work your way down the rows of A. So this entry will be the second row of A matched up with the first column of B. So I'll go 5 times 4, match up with 3, -2, so that gives me 15 minus 8 is 7. So now I match up to -3 with 3, -2. That gives me 6 plus 6 is 12. And so once I've gone through the entire matrix A matched up with the first column of B, I move on to the next column of B and do the same thing. So I'd match up -1, 2 with -2, 1. Give me 4. 5, 4 with -2, 1, so that'd be -10 plus 4 is -6. And finally, 2, -3, I'd get -7. So, matrix multiplication dance, you do that, match up rows and columns, and you get sort of, it's sort of similar to the vector dance. All right, so a few notes. A times B as a product is only valid. And so I think it's easier to see this when you imagine multiplying matrices for real. This is only valid if the number of columns of A is equal to the number of rows of B. So notice here A had 2 columns, B had 2 rows. And if you think about how the matching up process works, right? It's not going to make sense if A has too many columns that won't match up with the rows. So the way to tell this is that if A is, I'll do this in a different color to differentiate it. You look at the dimensions of the matrices. So if A is an M by N matrix and B is an N by P matrix, then A times B makes sense if this number and this number are the same. So that's how I always tell myself, can I multiply the two matrices? I check, do the sort of match them up, right? So A times B, if these numbers are equal, then I can multiply them. We're good. On top of that, we actually know the dimensions of A times B is always going to be M times P. I guess not equal, but so if the middle, sort of the middle dimensions, if you line them up like that, these two ends are the same, then we can multiply A and B, and that will always produce an M times P matrix. So that's when we can do it, the type of matrix we'll get. And so you can see here, A was a matrix with 3 rows and 2 columns, so it was 3 by 2. B was 2 by 2, and we got a 3 by 2 matrix. All right. So I want to do one more interesting example where we do a couple matrix products. Then I want to give a warning, and then we'll actually be done for this video. So, we're going to let matrix A be defined as follows. And B defined like this. So each of these matrices is a 2 by 2 matrix, right? So by the rule that I just erased, we can in fact multiply them. And what more, we can actually multiply them going either direction, right? So notice we can multiply A times B. And what do we get? Well, doing the dance, we match up 1, 2 with negative 2, 1. We get 0. Then 1, 2 with 0, 0. Or sorry, 1, 2 with 0, 0. And we get 0. Why am I? Sorry. I was doing it in a different order. Then we match up 0, 0 with negative 2, 1 to get 0. Then we match up 1, 2 with 0, 0 to get 0. And then we match up 0, 0 to get 0. Sorry about that. I was doing the matrix multiplication dance in a different order, and I was confusing myself. So I was going, yeah. Anyways, A times B is equal to 0, 0. All right, so that's cool. But like we said, we can actually calculate B times A. Let's see what we get when we do that. Well, so now I'm going to match up negative 2, 0 with 1, 0. And you might notice something interesting happening here. I mean, they get a negative 2 there. Now I'm going to match up 1, 0 with 1, 0. And get a 1. Well, then I'm going to match up negative 2, 0 with 2, 0 and get a negative 4. And then here I would get a 2. So notice A times B not equal to B times A. And this is actually one of the really interesting and cool things, because this is one of the only operations that we see in math that actually exhibits this property, that it is not commutative. Sometimes you do get matrices that commute, so sometimes you do get matrices such that A times B is equal to B times A, but in general it is not true. And so we're going to finish up with a few warnings about matrix multiplication. AB does not always equal BA. So that's one. And you can see this from the example. I actually chose this example because there's another interesting property that, all of the other types of sort of multiplying things we've ever defined, if, let's say x times y is equal to 0, right? And x times y, or x and y are just numbers. Well, if x times y is equal to 0, then you always know either x or y has to be 0. But notice here, A times B is equal to 0, right? But neither A or B is 0. So as you can see from this, just because A times B is equal to 0, that does not necessarily mean that either one of these matrices was the 0 matrix to begin with. And so sort of the stark contrast you can see, matrices and matrix multiplication acts very differently in some ways than normal multiplication of scalars, or even multiplication of, say, like scalars times a matrix. And one last property that I didn't get a chance to show an example of, we also can't really sort of divide matrices in the same way, and I'll show you what I mean. AC equals BC doesn't imply that B is equal to C. So this is another really, really, really big one, because this is something that should just feel true. Like the deepest parts of my soul want this statement to be true, that, if AC equals BC, then B has to equal C. But actually, I can give a very quick example here of why that's not true. So I'm going to let C be the 0 matrix, in fact. And so notice A times B is equal to the 0 matrix. Well, we know from our matrix multiplication, or just properties of multiplying, that anything times the 0 matrix is the 0 matrix. You could go through the matrix multiplication dance and verify that. But so notice here, A times B is equal to A times C, but B and C are definitely not equal. So just a few warnings. Really keep these in mind when you're working with matrices, because again, like a lot of these are properties that you'd be tempted to just assume, because they're properties that hold for real numbers and multiplying real numbers together. Unfortunately, they don't always hold with matrices. And so that will wrap up this video. We have one more of this section where I'll go over some properties and then introduce a few new ideas when it comes to working with matrices like this. But yeah, thanks for watching.